Hey there. When we're programming, there are all these incredible things happening just under the surface, kind of making our lives a whole lot easier. Today, we're going to pull back the curtain on one of the most important ones, the garbage collector. We'll be looking at a really clever idea called trace-based collection. So let's just dive right in.
So, let's start with a simple question. When you're writing code and your program is done with a piece of data, where does it actually go? I mean, every time you create a variable or an object, it takes up a little piece of memory. But what happens when you don't need it anymore? Who's supposed to clean that up?
Okay, here's a good way to think about it. Picture your program's memory like a big workspace. As your code is running, it's creating all sorts of things. Objects, data, leaving them all over the place. It's like a busy artist who grabs a new paintbrush for every stroke and then just drops it on the floor to grab another one.
Right, and as you can probably guess, if nobody ever cleans up that workspace, it gets messy, fast. Before you know it, there's no room left to work. And this is exactly the problem that led to the idea of garbage collection in the first place, this whole issue of the digital mess that comes from manual cleanup. So in some languages, like C++, you, the programmer, are in charge of all the cleanup. You have to manually free up memory for everything you create. And yeah, that gives you a ton of control, but wow, it is so easy to make mistakes. On the flip side, you've got languages like Java or Python, where the system just handles it for you. It's all automatic, which lets you focus on the fun part, actually building things.
So what kind of mistakes are we talking about? Well, for one, if you forget to clean something up, you get what's called a memory leak. Your program just keeps using up more and more memory until it runs out. But even worse, trying to use a piece of memory after you've already cleaned it up. That's a dangling pointer, and it can cause your program to crash in really strange and unpredictable ways. It's a total nightmare for developers.
And that's where this idea of an automatic janitor comes in. To deal with this whole digital mess, a lot of modern languages have something called a garbage collector. It's just this process that runs quietly in the background, keeping that memory workspace nice and tidy for us. So what is garbage collection really? It's pretty simple. It's a system that automatically figures out which pieces of data your program isn't using anymore, and then reclaims that memory space so it can be used for new stuff. That's it.
And this isn't some newfangled idea. Garbage collection has actually been around since way back in 1958 in a language called Lisp. It really took off in the 90s with languages like Java and Python. And today, it's basically essential. It's the hidden plumbing that lets us build all the complex software we use every day without getting lost in the weeds of memory management.
Okay, but this brings up a really cool question, right? If this whole thing is automatic, how does the computer know? How does it decide what's garbage and what's still important to our program? I mean, how can it tell?
Well, the answer is based on this really elegant idea called reachability. And here's the clever part. Instead of trying to find the garbage, the collector does the complete opposite. It looks for everything that's not garbage, everything our program can still get to.
So, the whole search has to start somewhere. It begins with something called the root set. You can think of these as the things your program can definitely, directly access right now. We're talking about stuff like global variables or whatever is active on the call stack. These are the starting points. From there, it's pretty cool. The collector starts at that root set and just, follows the connections. It follows every reference from one object to the next, almost like following a web of strings. Anything it can get to by following these paths is considered reachable. The logic is, hey, if you can still reach it, it must still be in use.
And that's the whole game, right there. The garbage collector's entire job is to find everything that's reachable. And once it's done that, well, anything left over, anything it couldn't reach, is, by definition, garbage.
So, how does this actually work in practice? Let's look at one of the first and most basic methods that uses this idea. It's called mark and sweep, and it's a really simple two-step process.
First up, you have the mark phase. This is exactly what we just talked about. The collector starts from the roots, follows all the paths, and puts a little mark on every reachable object it finds. Simple enough. Then comes the sweep phase. The collector just goes through all of memory from top to bottom. If it sees an object that doesn't have a mark, it knows it's garbage and frees up that space. Now, mark and sweep works, for sure, but it has one little problem. Over time, your memory can get fragmented. you end up with all these little pockets of free space in between the objects you're still using. It's kind of like a checkerboard. And that makes it really hard to find a big, continuous block of memory when you need to create a large new object. So, to fix that fragmentation problem, people came up with even smarter collectors. These don't just clean up the garbage, they also tidy everything up. And this is where we get into things like compacting and copying collectors. The idea here is just beautiful in its simplicity. It's like, okay, we've already figured out which objects we want to keep. So, why leave them scattered all over the place? What if we just move them all together? And a really clever way to do this is with what's called a copying collector. The way it works is it divides the memory into two equal halves. Let's call one the from space and the other the to space. So here's what happens. Your program is running along creating objects in the from space. Once that space gets full, the collector wakes up. It finds all the reachable objects just like before, but instead of marking them, it copies them over to the empty to space, all packed together nice and neat at the beginning. Once that's done, the entire from space is now empty, and the to spaces just swap roles. It's so elegant.
And this approach of tidying things up, it has some huge advantages. First off, fragmentation is just gone. You always have one big, continuous chunk of free memory, which makes allocating new objects super fast. It also tends to group related objects together, which is great for your computer's memory cache and can make your whole program run faster.
And this is the kind of invisible work that's happening behind the scenes, all the time, in languages you probably use every day. We're talking Java, Python, and many others. They all depend on these smart garbage collectors to keep things running smoothly, so we can just focus on our code.
You know, there's this idea that the best tools aren't the ones that help you solve problems, but the ones that prevent the problems from ever happening. And that, I think, is a perfect way to describe garbage collection. It doesn't just help you find memory leaks. It makes that whole category of bug basically impossible.
So the next time you're writing some code, maybe just take a second to think about that quiet, automatic janitor working in the background. It's always there, keeping things clean, so you can focus on the important stuff, being creative and building amazing things. Thanks so much for watching.